the lecture 6, which is directly dedicated to the topic of program analysis. This entire course is about program analysis. We discussed things which can help us understand programs, understand their semantic, understand their syntax. Today we will see how people suggest that we do the analysis of those programs. How can we look at the qualities of programs, of the properties of the programs, in order to understand what they do and whether they do what we want them to do or they do something else. This is the contents of the course, of the lecture. Let's start with the basics. The properties. There are semantic and syntactic properties of a program. The semantic property is different from a syntactic property, is that they can be detected when we look at the program. We can understand whether the program has certain property, whether by running the program or by looking at the program. So if we look at the program, then this property is called a syntactic property. So we just observe the text of it and decide whether the program has certain property. It doesn't mean that the program evaluates to some number, to some result, or the program works certain way. It could be different properties. Something we can tell about the program. And the property is semantic, is called semantic, if we need to evaluate it in order to understand whether the property actually is there in the program. So I suggest you to look at this program and try to tell me which of the following 4 properties which are listed here are actually dynamic properties. The dynamic or semantic, which I call them dynamic here, so probably it's more maybe a typo, but I think it may be called this way. So which of them we can tell only by running the program? So let's take a look at the first one. A program may print a text to the console. So by looking at this code, we cannot. I'm not sure. I'm not sure I will be 100% right here, but I suggest that the first property is syntactic. So we do not need to run this code in order to say that the program may print a text to the console. So X may be true, X may be false, we don't know, but there is the possibility that the text will be printed to the console. The second one, a program may call printfc function. The same. As long as we say may, it means that it's possible that the execution will be there, so the call will happen. So we can say this is also a syntactic property, as far as I understand it. The number 3, a program prints to the console. So in this case, we say that the program will definitely, when it is executed, it will print something to the console. This we cannot say. By looking at this code, we cannot say whether true or false. We need to actually run it. We need to actually look at the behavior of the code in order to decide. So this one, I believe this is dynamic or semantic, something like this. And number 4, a program consists of 1 line of code. Of course, this is also syntactic. So we can say that this code has exactly 1 line of code. And we can, into these properties, we can send other programs, program 1, program 2, program 3, and we can check whether these programs actually have certain properties. So all this program analysis, which we're going to discuss today and in the next few lectures, is all about detecting the properties of a program. So we don't want to get a program and then run it multiple times in order to understand how it behaves. We want this decision to be made somehow before we run the program, or maybe after we run the program, but we want these decisions to be made in a generic way for different classes of programs. Not on the one specific program, but in general, create, for example, the program analyzers, a software which will look at the program which we have and tell us that this program, for example, will fail if you run it, with this particular input data, then the program will fail. So this is all, that's what the program analysis is about making the decision of which properties are in the program. There is a theorem which says, a very famous theorem called Rice theorem by the name of the scientist who suggested this theorem. It says that all non-trivial semantic properties are undecidable. Undecidable means that we cannot really create a decision maker, automated, which will look at any particular program and tell us whether this semantic property is there or not. For example, we had the property before. The program will print something to the console. So the theorem says that you cannot create such an analyzer which will accept my program and will tell me whether this program prints to the console or doesn't print to the console. And they say that the property is non-trivial if it's neither true, it is neither true for every particular computable function or false for every partial computable function. So they say that non-trivial means that you cannot, it's not always true and it's not always false. So for example, let's say the property is, let's say you can say the property, I'm trying to invent the property which is always true. So let's say a program that has to be semantic property. So let's say a program will run longer than 1 nanosecond on this computer, which is, for example, quite slow. So no matter what is the program, we definitely know that it's going to be, it will run, even if the program exits immediately, then it's still going to take a few microseconds, for example. So this is non-trivial property. So on this one, you can't prove. You can't create a decider, automated analyzer, which will look at the program and will tell you true or false. But if the property is non-trivial, then it could be true, could be false, then it's not decidable. How they prove this theorem, you can read yourself. It's not so complicated, but they are the proof of this theorem is based on the definition of, probably you know, the halting problem, which is the problem of determining whether, by looking at the description of the program and by looking at the input for the program, we say that it's not possible to design a system, an analyzer, which will look at the description of the text of the program and look at the input, and it will automatically say whether this program will stop at some point of time, the execution, or it will run forever. So this is so-called halting problem, which is one of the fundamental problems in computing, and it is proved that it is not possible. So you cannot create such an algorithm, and pay attention, general algorithm, which will take any program and it will say, okay, I know that this program will eventually stop, and this one will not. That is not possible, and because this is not possible, this theorem is also true, because you cannot understand whether the program will stop or not. Because of that, you cannot really decide on any non-trivial semantic property. So why I'm telling you this? Because to explain you that you cannot really make a static analyzer or any analyzer of a program which will be making decisions certainly, with 100% certainty. You can only make some approximation. You can only say that my analyzer, which will look at the program, will say that there are bugs in there, that will say that the problems are there, but it will only make it for certain cases, not for any program, not for all cases, because it's theoretically not possible. Examples of non-trivial properties. Yeah, I was trying to give you a few. Let me give you a few more. Let's say a program exits. We just discussed that. So this is one of the non-trivial properties. A program, at some point, it exits. So there will be no endless loop in the program. Let's say a program says hello. It's another property. A program finishes in less than 5 seconds. It's another non-trivial property. Some programs, they end in 5 seconds, some programs not. A program dies with segmentation fault. This is one we are maybe particularly interested in a static analysis, because it's very practical. These three, that's mostly for fun, but this one is really practical. So we want to know whether the program will fail with a segmentation fault. So it's abnormal termination. And if you create such an analyzer, which will look at the arbitrary C++ program and will say, yeah, I believe that at some point of time there will be segmentation fault, then people will pay a lot of money for this software to you, because it will help programmers actually develop software better if you can decide on this non-trivial property. Of course, like I just said, you will not be able to decide for all situations. You will not be able to make it your analyzer powerful, so powerful that it will make this decision for any software. But for some, you can do that. Another example, a program prints user password to the console. Another very useful example. This is security issue. So this is like a functionality bug, and this one is security bug. Again, if you design a software which can make this decision on any or on most programs, then you can make quite a lot of you can help a lot of people. I suggest you to think about other properties, and you can think about what else you can decide about programs. Static analysis. So what is exactly static analysis? Take a look at these two programs. On the left, they're both C++, so I would say C even. So there are two programs on the left, on the right. They look at what they do. So the left one, it just says that x equals to 0 and it returns 42 divided by x. The right one accepts x as a parameter and also divides 42 by x and returns the result. So if you give these two programs to Clunk Tidy static analyzer, Clunk Tidy is quite popular open source static analyzer for C and C++ code. You can download it yourself, install it, and try to use it. And if you give this program on the left or the program on the right to Clunk Tidy, you're going to get two different answers. For the program on the left, this analyzer will tell you that there is a bug there. So it will tell you that when you execute the program, you're going to get division by 0, mistake, error. And this answer from static analyzer I consider as a yes answer. So the analyzer is supposed to tell you, is supposed to find problems. So the properties which an analyzer detects, the semantic property, non-trivial semantic property, is whether the program will fail with a mistake, with an error message or not. So if the analyzer says yes, it means the analyzer says, yes, I see this property, I see that the program will fail with a bug. So that's why it's in green color. So static analyzer is not telling you that everything will be fine. The analyzer successfully executes when it says the bug is there. So the bug is detected, it means yes. The answer no means I did not manage to find a problem in this program. But we know that no doesn't mean that the bug is not there, because we remember about this Rice theorem, which says that it's not possible to create such an analyzer which will say no for sure. So if no means that most probably, or not most probably, but 100%, the bug is still there, some bugs. Because making a static analyzer 100% sure is not technically possible, not even theoretically possible. So two examples, two programs. Static analysis is about detecting bugs before you run the program. We didn't run these two pieces of code. I didn't run them, even though I did that to check that actually they work. But actually they're not even, these two codes are not even runnable, because there is no main function, so you cannot just compile it and run them. So they are just definitions of two functions in C language or C++. They're just declarations of functions. These are not even programs which you can run. But the static analyzer tells me something is wrong there. And these tools are very powerful and very important for the business. So if you go to any more or less serious company with doing some serious software development and some mission critical software, then they definitely use static analyzers. So they use tools which check their code before the code goes to production. They check the code, and the tools, they tell them where are the bugs. Of course, it's not so easy. The tools may sometimes make mistakes, and we're going to discuss today how these mistakes are treated, how they should be treated. But in general, pay attention. Static analysis is a super important aspect of any serious software development nowadays. There's also style checking, which people sometimes confuse with static analysis. So I decided to show you the difference so you understand, so you don't mix them, these two concepts, you don't mix them. Static analysis is telling a programmer where the semantic property, telling the programmer whether the semantic property is there, whether the program has this property. Style checking is about syntactic property. So style checking is looking at two different programs, for example, this one and that one, and it tells you what's wrong with the text, even though both examples, the left and the right, they both compile, they both work. However, the left one is formatted the wrong way. So the Clang, not the Clang, CPP-lint. So I'm using CPP-lint. This is again another open source style checker, which you can also download and install and use. You ask this style checker to look at your code, and CPP-lint will show you two problems. We'll say that there is an extra space before the function call, and that the opening curly bracket has to be at the end of the previous line. So basically, this is the code which is okay for CPP-lint, and this one is not okay. But again, look at the colors I'm using here. So the green color is here and the red color is there, meaning that the style checker, when the property is there, and the property is the problem. So all of these guys, style checkers, static analyzers, they are supposed to find problems, and problems equals to properties. So the property of a program is that it is written in the wrong way. So the code of the program is formatted the wrong way. So style checkers, they check that. It's necessary to use them both. So you should put them together. Static analysis and style checking, they're two different things, and they should, in a good project, they should work together. And finally, what you need to know about this classification of tools is dynamic analysis. So we have static analysis, we have style checkers, and we have dynamic analysis. Dynamic analysis is very similar to testing. I even put it this way. So dynamic analysis is basically running the code and seeing how it behaves with certain given input data. So we want to know what's going to happen with the program after we execute it. So look at the code on the left. So this is a very simple piece of C code. If you understand C, you should understand what it does. And this is executable code. So this one you can just take as it is from here, compile using any C compiler. It will compile, you can run, and it will work. When you compile and run, you're gonna get an error. You're gonna get segmentation fault error or something like this. Why? You probably understand, because here in this function foo, we allocate an array of 5 elements, and then we're trying to get the element by the index I, and the index I is coming as an argument from here, and here we pass the argument 6. So it means that we're gonna jump off the memory space, the territory in memory, which we're allowed to stay in. So we're trying to access the memory outside of this territory, and because of that, the evaluation environment will stop the program, will terminate the program because of this fatal error. There are instruments for dynamic analysis which help you understand why the problem happens. So for example, you can use together in C++ for the dynamic analysis, you can use so-called address sanitizer. So this address sanitizer is the plugin for most popular compilers. It goes for GCC, for GCC, for Clang, for Microsoft compiler. It is plugin developed by Google or in Google. So you use this plugin inside the compiler, and because of this plugin, the output of your code will look like this. So it's not going to be just segmentation fault, it will be a more detailed description of what the problem is in the code. So it will show you that it will show you the line of code. You see ACPP, the line number 9. It will explain where it's coming from in the main class, in the main function. So it's going to be more detailed information, and it will also explain to you what happened. It will explain you why this segmentation fault is happening. It will say memory access at offset overflows this variable. So you get the detailed information. In order to have this sanitizer, all you do is that you compile your code using these flags. So this is dynamic analysis. So it's just an instrument which stay with you while you do the testing, while you run the program with different arguments and see what happens. This is dynamic analysis. It's very close to testing, but just maybe a more fancy name and more like a technology. Even when testing is more like a procedure, like a feature of your development. So that's it for the introduction part, and now let's go into how we can measure the analysis. How can we, as I said, the analysis cannot be perfect. It's impossible to create a tool which will do a perfect job, which will always tell you that the bug is there, or will always tell you that that this feature, that this program will exit on this condition, that the program will reveal some security information or something like that. It's not possible. So what is possible? There are two very important things which you need to really understand about analysis of programs, not only static analysis, but in general analysis of anything, but it's applicable to program analysis. Soundness and completeness. There are two properties which are sometimes, you need to understand it. I'm not saying it's difficult to understand them, but you need to understand them. So look at this picture. This picture helps me. I made this picture for myself, so maybe it will help you as well. So look at it. On the left side, we have the reports of the bugs. So let's say we come to the tool. I give my program to, I give a number of programs. I wrote a number of programs, and I give these programs to my analyzer, and I ask the analyzer, what do you think about this program? So I give this analyzer 3 programs. This is 1, this is 2, this is 3. And it gives me, actually I give 4. 1, 2, 3, 4. So I give like 3 experiments. So I run 3 experiments. In these 2 experiments, and all the time the analyzer tells me that the bug is there or not. And in this case, the tool says, no, there is no bug. And here the tool says, yes, there is a bug. And here the tool says, yes, there is a bug. And here as well, it says there is a bug. But in reality, the bugs were here, here, and here. So this was a missed bug. So the bug was not discovered. And this calls false negative. So the answer was negative from the analyzer. I asked the analyzer, do you see the bug? And the analyzer said, no, I don't see the bug. So I give you negative answer. My answer is negative. Is there a bug? The answer is negative, no bug, but this is false. That's why it's called false negative. So the analyzer gave me false negative response. And here, the analyzer said, yes, the bug is here. But in reality, there was no bug. So I gave the program without a bug. But the analyzer said, yes, the bug is there. So the analyzer gave me the positive response. I see the bug, I see the property, I see that this program will fail, but it's false. The information is wrong. So it's called false positive. And this is okay. This is true positive information. So this this is true positive. So the report is here, the bug is there. The report is here, the bug is here. Maybe you can also, it doesn't stay here on the picture, but let's say the answer is no, and there is no bug as well. So we would call this true negative. So the answer is negative and it's true negative. So there are 4 possible answers. We call them true positive, true negative, false positive, false negative. 4 situations how the analyzer can respond to our experiment. And of course, where true, this is good, and this is bad. So we don't want to have false negative, false positive, and false negative. We only want to have true positive and true negative. So the analysis is called sound. The sound analysis is when we don't have this, when we don't have false positive. So this is unsound situation. Why it's called sound? Because imagine there's a song, and the song is this, but this is noise. So this is unsound, means noise. So we're asking you to give a clear answer. We're asking you for true positive or true negative, whatever. But we don't want false positive. So false positive, you kind of add more information. You add more noise to the flow of information. So you're telling me like this is. Let's say you would be, I don't know, you would be driving a car and somebody would be sitting next to you with the map and telling you like we should go straight, then we should turn right, then we should turn left. And sometimes this person will give you wrong suggestions. Will say, hey, turn right. And then, oh, sorry, I'm wrong, turn left. Okay, you go first and they say, oh, turn left. No, wait, turn right. So that would be noise for you. You would say like your information is unsound. So please be more sound. So clear your information, make it look more sound. And the second problem is incompleteness. So this is incompleteness. It means that, let's say again, the bug was there, but you didn't tell me about the bug. That would be like you're driving a car and the person next to you sitting there, and it was necessary to turn right, but the guy was quiet, no information, just sitting and I don't know, checking his phone. And you would say, you're not complete, your information is incomplete, so please tell me when to turn, because I missed the turn, because you stay quiet. So don't be unsound and don't be incomplete. That's 2 fundamental properties of any analyzer, any of any tool which is supposed to reply differently to you. Which is supposed to say yes or no to certain information which you provide. So get it into your head, because it's very important. I mean, there will be there will be many times when people will refer to these terms, soundness and completeness, and you have to understand what's the difference. So like I said, think about this information provider, the guy with the map. The guy has to be sound and it has to be complete. So don't miss the turn, be complete, and don't give me false turns. So be sound. And now let's see, and there is also another 2 more measurable things, how people measure the soundness and completeness. So people say that the soundness means that the analyzer is sound, meaning that there's 100%, there is no false positive signals from the analyzer. So every time I give the program to the analyzer and I ask the analyzer, is there a bug? And the analyzer says, yes, there is a bug. And this is always true. So there will be no false positive, no false information about the bugs. There will be no situations when the analyzer says, yes, there is a bug, but in reality there is no bug. So they call it the precision of the analyzer. The precision is how many mistakes the analyzer makes. So it's not enough to say sound or not sound, because unsound or not sound means that it's not 100%. And sound means it's 100%. But we want a more clear, a more fine-grained measuring of this quality of the analyzer. That's why we use precision. So precision is basically calculated using this formula. So we can take the amount of true positive and we divide it by the amount of true positive plus the amount of false positive. So basically, this is at the bottom we see the total amount of positives. So when I talk to the analyzer gave me 100 answers positively. 100 times the analyzer said, yes, there is a bug. So the question is, how many of them were true? and only 70 of them, they were true. So we say the precision of this analyzer is just 70%. And there's another property which is called recall. Recall is, as you may guess already, it's the same but for the completeness. For the completeness, we take a look at the bottom part here, and we see, okay, there's a true positive plus false negative. So in this case, we take a look at how many, the true positive still stays at the top, but at the bottom we see true positive information and false negative. So it means that we summarize the good answers at the bottom plus the true positive plus false negative. So we summarize this part here. Let's see on the picture, it'll be easier. So we put together all of these guys, because these are true positive and this is false negative. And in this group, we see how many of them, what's the relationship between this and this. So we want to see, ideally, we want to see that this is 100%. It means that this is true positive. Sorry, this is false positive. So we divide. We want to see how big is this part in this entire output of the analyzer. So the analyzer is giving us 100 answers, for example. So out of this 100 answers, the total amount of answers was 100, and out of them was, for example, 70 which were true, and these were, the 30 of them were false negative. So it means that the answer was the analyzer is complete only for the recall is only 70%. So 100% recall means 100% means completeness, means that the analyzer is complete. We will now play with these numbers, and you will see some. You will see how they fit together. And also there are also two other metrics which you may find interesting. There is accuracy and F1. Accuracy is you put together all the good answers, true positive, true negative. They're both interesting answers. We're both interested in them. And then you put at the bottom everything. So you put all the different categories of answers, all four. So basically this is everything which came out of the experiments, and this is the good part of the experiment. I find this metric the most interesting. So me personally, I would pay attention to this one. But usually people instead, they work with precision and they work with recall. But I see this one as more accurate metric. So accuracy means that what was the actual value of the entire process. So if the good answers constituted, I don't know, 75% of the entire set of answers, and this is our value. So that means the analyzer is 70%, 75% accurate. It gives true answers in 75% of the time. And F1 measure is you can learn it yourself. I mean, I'm not using it in my work, so I just put you the formula. You can study what it's for. But we will actually calculate it right now. So let's take a look. Imagine we have an experiment where we are trying to understand how good is our analyzer. So in order to do that, we give to our analyzer 8 programs, 8 cases. A, B, C, D, E, F, G, H. There are 8 programs which we ask the analyzer to test. And we know that 4 of them, which are green, they have bugs. And 4 of them which are red, they don't have bugs. Again, why I use these colors, why I call green as bug? Because, let me remind again, I expect the analyzer to tell me something, to find the property if the bug is there. So success of the analyzer is the bug is there. So the analyzer says, I find it, I got it, I know there is a bug. It's a successful answer from the analyzer. That's why it's a green color. Okay, and then at the under these rectangles, we see the actual answers of the analyzer. So in this case, analyzer says for the A, the analyzer says yes, the bug is, the analyzer actually says that yes, I found the bug. Here it says yes, I found the bug. Here it says no, I don't see any bugs. And then here it says yes, I find any bugs, and so on and so forth. So the answers you see and the expectations you see. And now let's calculate. So true positive, how many true positive we see here? I guess 1, A, B, and D. True positive answer. 3. How many we have false positive answers? 1 and 2. So this is the positive answer, but it's false. So the answer was yes, but in reality it's not true. So we have 2 false positive answers. How many true negative we have? True negative answers. This one, 1 and 2. So the analyzer gave 2 negative answers. This is negative, and in reality it was true. So it's true negative answers, only 2. And how many false negative? Only 1. So these are the numbers we collected from the experiment. This is the observation. And now let's calculate the metrics. So what is the precision of our analyzer? It's, I guess, 3 divided by 3 plus 2. Which would be, you can calculate it yourself. Recall, in this case, true positive, 3 divided by 3 plus 1. Accuracy. You can do it yourself when you have time. You get the idea, right? That's how we measure analyzers. There's no rocket science, nothing difficult, but you just need to understand what are these magic words actually mean. Like true positive, true negative, and so on and so forth. The question usually, when you test the analyzer, the problem is how to design this set of tests, set of experiments. This is the most difficult part, I believe, because like we know, the properties are not so trivial, and it's hard to design the piece of code so that when you give it to the analyzer will be able to or not be able to detect the problem in an isolated way. Because usually the problems, they go in together with other problems. And if you want to, let's say, like we had before an example of the dynamic analysis, when we had this out of memory problem, then it's a question how to design that piece of code so that the analyzer look at it and will be able to find just this particular problem. And by the way, you know, I forgot to tell you, by the way, this problem with the dynamic analysis, which I showed you here, it is not detectable by clunk tidy, for example. So if you give this code to clunk tidy, then it will tell you that there is no problem. So this code goes into clunk tidy, a static analyzer, and static analyzer gives me the false negative information. It says there is no bug, there will be no memory access, no illegal memory access will happen in this code. So it's obviously a false negative answer from clunk tidy. But this is a very primitive piece of code. So if you create your own analyzer, you will need to design your experiments, you will need to design these pieces of code, which you will feed to the analyzer, and it will be a problem for you how to do it. Because in this, like this simple you can do, but larger pieces, larger code snippets, you can actually get from existing data sets with these primitive programs which you can use to test your analyzer. And you can Google it, or you can find, for example, one of the data sets which I know is called Juliet. It's a open, not open source, it's open. It's a free public collection of C and C++ pieces of the code, and each piece of the code has a bug or a number of bugs. So when you design your analyzer, you will be interested to know what is the accuracy, what is the precision, what is the completeness, what is the recall of your analyzers. You will want to calculate the parameters, the qualities of your analyzer. You can download this data set. There will be, I guess, 20,000 code snippets. So there are thousands of them. And your experiment will not look like this, not like 8 pieces of the code, but there will be 20,000 C++ code snippets. Then you give them to your analyzer, you collect the answers from the analyzer, and you can claim that my analyzer is, the precision of the analyzer is this and that, which is higher than, for example, another analyzer. And that's why, please buy my software, please pay me, don't pay them because I'm better. And that's going to be your argument if you try to make your analyzer compatible with with other products on the market. And these are the main parameters, not only precision. There will be more parameters, but overall these numbers will be the most important to consider. And of course, you will have to say that this true positive, it happens on this particular data set. So it's not going to be just one number. It's not going to be just 3, 2, and then something like that. You will have to explain in more details. You will have to say, where did you get the data set? Which particular parts of the data set you were using? How many of these experiments you were running? So N was, in this case, it was 8, but in your case, it's going to be 1,000. So all of these numbers will be important. And finally, to finish this section, I'm going to tell you some interesting story about the terminology, which can be flipped sometimes. So for example, if you read a blog post, very interesting, very good blog post by Professor Bertrand Meyer, he published, I think, a few years ago, he explains the soundness and completeness, these things which were just discussed. What's the difference between soundness and completeness? And there is I quote from there. He says, it's very easy to obtain soundness if we forsake completeness, so if we ignore completeness. So in order to make our analyzer sound, we need to, according to his words, we reject every case. Reject every case. But in our understanding here, in order to make our analyzer sound, and sound here means, let's recall this, the precision must be 100%. So in order to make our analyzer sound, we need to have false positives, 0. In order to make the analysis sound, we can just and always have no false positive, no false positive. The easiest way is to just never give any positive answer. So we just say no, 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 and no. The analysis will be sound because no noise. So imagine this guy sitting next to you in the car telling you nothing. It's absolutely sound. So there's no noise coming from him. It's incomplete 100%, but it's 100% sound. So no information means sound analysis. So we say in each case, we say no bugs. So everything is okay. But now the question is, what does it mean reject every case? How can we interpret this word, reject any case? Reject means, in terms of static analysis, it probably means that you say that we don't like this program, we reject this software. It means that we say that there's a bug. So it's kind of the opposite. So the question is, it was very confusing for me, to be honest. A number of months ago, I was writing a paper on this in this area, and I was trying to put together this like these soundness and completeness elements in relation to static analysis. And I found a number of papers, a number of articles explaining this, including this blog post of Professor Mayer, where he says reject. And I wasn't able to understand, like, why are you suggesting rejecting? In case of, to make analysis sound, instead, the analyzer should accept every case, should say, yeah, okay, like, no problem, no bugs here, like, go through. So the question is, if you understand, it all depends on how you understand the answers from the analyzer. So if you treat your analysis, if you treat the analyzer, the answer from the analyzer, when the bug is found, you treat it as a positive answer, then you have your soundness and completeness defined one way. But if you treat the answer from the analyzer, if the bug is found as a negative answer, like some people do, you may find that in literature, you may find it on the internet, and people say that analyzer, when the analyzer finds bug, it's a negative answer. So in this case, everything will be flipped upside down. So the precision will be defined differently, the recall will be defined differently, all the terms will be flipped upside down. So in this case, the soundness will mean, will be calculated using the opposite formula, and not the soundness, the precision and the recall. So all these true positive, true negative, they will switch places. So don't be confused. That's my point. So when you read about this soundness and completeness, the first question you ask is what the author is calling the positive answer. So for the author of this paper, what is a positive answer from the analyzer? And if the positive answer, like for me, is when the bug is found, then you have the terminology which I presented to you. But if the author understands the answer from the analyzer differently, the opposite way, then the terminology will be defined also in an opposite way. Keep it in mind, that's important. I mean, that confused me a lot, so don't be confused as well. So remember that we need to understand first what is a positive answer. Next step, we're gonna discuss today abstract interpretation, which is the foundation of static analysis. Next lectures, we're gonna discuss data flow analysis, symbolic execution, and model checking. But today we stay with the abstract interpretation. Abstract interpretation, as they say, as it is a foundation for the analysis, because it allows us to analyze the program in an abstract way, without the concrete execution, without analyzing concrete numbers and concrete inputs and concrete outputs. We just look at the program as an abstract evaluation machine, and we decide whether this machine will fail or not, whether it will return this number in general, this group of numbers, or it will never return this group of numbers. In order to do this analysis, we start with a so-called lattice. That's a mathematical structure which they use a lot. So that's why I decided to explain you this concept. Maybe you know about this from your other courses, but still I'll spend 10 minutes on that. Before we go to the lattice, we need to understand what is the total order. The total order is the binary relation on a set. So let's say you have a set of numbers, and this set of numbers, there is a binary relation defined on this set of numbers. It means that between every two number, there is a relation defined by, let's say, this symbol. So we can compare every two numbers in the set, and the result of the comparison will tell us which number goes left or goes right. So it's possible to compare them. So the result of the comparison is known. So we can take any two elements from the set, and they are comparable, and we know what's the result of the comparison. So look at these 5 sets, and tell me which of them are so-called law sets, linearly ordered set. Linearly ordered set is basically a set with a total order. So it's a set where every two elements are comparable, and we know the result of this comparison. So first one, what do you think about this? Is it a law set or no? I believe it is, because all of them are numbers, we can compare every one of them. Everything is fine. So this is low set. What do you think about this one? It's a bit more tricky because it's not really a set, because we have two duplicate elements here, 5 and 5. So it's not even a low set, it's just not a set, because we have duplicates. And a set means that all elements are unique. So this is not a low set, this is yes. This one I believe is not a low set, because you cannot compare 5.0 with, for example, 3. And you cannot compare hello with, for example, 5. I mean, in my world, maybe you can, but by just looking at this set, we can say that no, they're not comparable. So this is not a linearly ordered set. This one, it's a question. I don't know. X, Y, Z, do we know how to compare them? Do we not know? I don't know. It's unclear to me. So it depends on whether this binary relation exists, whether it's defined somewhere. If, for example, we define it and say, for example, X is less than Y, and Y is less than Z, and X is less than Z, then probably that's it. Yeah, that will be enough. So if we define these relations, and this is true, this is true, this is true, then this is a low set. What about this one? Empty set. Yeah, of course, no elements, so empty set is a low set. So just remember, this is called total order. There's also so-called partially ordered set, POSET, partially ordered set. Partially ordered set is the same, but we don't need to compare every two elements, only between some elements. So some of them are comparable, some of them are not comparable. So let's take a look at the example. This one, 1, apple. So apple and orange are comparable. 2, -7, and 1 are also comparable. So that's a perfect POSET for us. Some of them are comparable, some of them are not comparable. What about this one? Again, the same problem, 5 and 5, it's not a set. What about this one? That's an endless set, starting from 0 and goes up to infinity. 1, 2, 3, 4. Is it a POSET? Yes, it is. They can be, it's never said that the set is finite, so it may be infinite set. Infinite set is also a POSET. And actually it's a total, it's a low set. It's even stricter, because all the elements are comparable, all of them. So it's an infinite low set. What about this one? Again, we don't know about X, Y, Z, but even if we don't know, let's say they're not comparable, none of them are comparable, it is still a POSET, even if none of them are comparable between each other. And this one, of course, empty set, the same. Okay, so now you know what is a POSET, now you know what is a low set. And now the lattice. Lattice is a POSET, so it's a set where some of the elements are comparable. And there's an interesting quality which must be present in the lattice. Every two elements, they must have a so-called least upper bound and a greatest lower bound. So for any two elements of the POSET, I should be able to find an element which stays, if we put it graphically, then it stays on top of them. If we put all elements of the POSET from the lowest going up to the biggest, then for any two elements I should be able to find the element which stays on top of them, and should be only one of them. So let me give you by a real example on the graph. So let's go from the left to the right. So this is a POSET. A POSET which consists of 1, 2, 3 elements, 3 numbers. And I position them vertically, like I promised you, where the lowest one stays at the bottom, the biggest one. What do you mean lowest? What do I mean lowest? You remember that the POSET is a set equipped with this operator, where some of the elements are comparable. So I'm saying this is here and this is here. So 2, basically 2 is less than 13. 13 is less than 42. So this line means that I can compare these two guys with this element. Well, actually I can compare as well. like this. I just didn't draw this line by mistake. So in order to say what is the least upper bound, so what is the between any two elements, it means that we take any two elements. For example, let's take element 2 and element 42. So what is the 42 and 2? Least upper bound is defined by this operator. So between these two numbers, which one of them is the lowest possible to both of them? It's 42. That's clear here because, you know, two numbers, so it's just easy to understand. It's trivial. Let's take a look at the second example. This is the poset, the A719B. So A and B, they are comparable somehow. And then 1 and 19 is also comparable. So we have visually it will look like this. So now the question is, can we find the least upper bound between the elements A and between 7? So can we find on this graph some element which stays above them both and we can reach it from each of them? No, it's not possible because nothing is there. So basically it's empty set. And because of this is empty set, this is not a lattice. Because I cannot find an element, a least upper bound, and I cannot find the greatest lower bound. So if I take, for example, element B and element, let's say 7, then I cannot say B7 is also an empty set. So no elements which can be called greatest lower bound. They are, by the way, these operators, they're called a join operator and meet operator. So the join operator is where we join when we go up, and meet operator where we meet if we go down on the graph. Okay, let's take this example. So the question is it a poset? Is it a lattice, sorry? This is our set, A, 9, B. So these symbols are, it means everything and it means nothing. That's how they put it on the, that's what they use on the lattice. So this one is the top, the symbol called top, which means everything, and this symbol is bottom, which means nothing. So let's say we put it like this. So we know that we can put these symbols here. So nothing is less than 9. It's less than everything, and nothing is less than A, and A is less than B, and B is less than everything. So everything is like, or the largest, this is the, not everything, maybe largest, and this is the smallest of everything, this is largest of everything. So they form this graph. And now the question is, what is the least upper bound of A and 9? A and 9. So we go up, and we meet here. We join here, sorry, we join here. So here, the least upper bound is this bottom symbol, the top symbol. So what is the greatest lower bound between B and 9? Okay, we go down and we meet at the bottom. So this element is the bottom. So this is a lattice, a perfect lattice. The final question about this one, what do you think about this one? Is it a lattice? We have 6 elements in the set. The top, the bottom, A, B, C, D. So let's put them on the graph. So this is the top stays at the top always, this stays at the bottom, because this one means everything, includes everything, or more than everything. It's always above everybody. And this is always below everybody. So A, and let's say this is the relationship which we define on the poset. So we can compare D and C, we can compare this and this, we can compare B and C, we can compare D and A. So we have this, they're all comparable between each other. They can be compared. Let's say, I can give you an example. Let's say there are numbers. Let's say this is 9, this is, I don't know, 7, this is 3, this is 17. So 7 is less than 17, 3 is less than 9. Even here we can put the connection like this, and we can put like this. So they're all connected to each other. But let's remove that and let's imagine we have this graph. The question is it a lattice? So let's find a least upper bound between B and D. B and D. So if we go up, we're gonna join here, or we can join here. So in this case, it's like A and C, but there could be only one. That's why it's called least upper bound. Not upper bounds, not many upper bounds, but least. And in this case, in case of this, on this graph, it's not possible to find least upper bound. And the same problem if we go down and we try to meet from, for example, A and C. From A and C, we go down, we meet here, or we go down and we meet here. So because it's not possible to find least upper bound or greatest lower bound, that's why this is not a lattice. So that's it. That's the idea of lattices. So lattice is a poset which has this property. So it is pretty well structured. So from any 2 points in the lattice, you can go up and join, you can go down and meet. And now let's see how these graph structures, how these sets actually presented as graphs can be used in static analysis. But before, one more example. So a lattice may be defined, and which is usually how it is used in static analysis, is by using intervals. So intervals are used as elements, or intervals, or maybe we can call them not even intervals, but subsets. So it's very useful to use lattice when you want to define relationship between different sets or subsets inside a larger set. So on the top you position a largest set, a biggest set, which includes everything, and at the bottom you position empty set, nothing. And then you define relationship in this lattice with this operator. A set includes, belongs, or is a subset of a bigger set. For example, the set on the top I defined basically all numbers. Let's put it this way. And then here I defined all negative numbers, n with the subscript n. And then here I defined a subset or a set with just one element 0. And then here from 0 to the infinity. So we can say like this. So that means that n is in n big. Then n minus belongs to this, and 0 belongs to this. So they're all these three subsets are, these three sets are the subsets of the largest set. And here I can break it down into parts. Let's say these are odd numbers, and these are even numbers. And these are the numbers which are 2 power x. So the even numbers and odd numbers, they both belong, they both in the into this set. And then this one definitely is a subset of this one. And then empty is a subset of all of them. So this is a lattice, as you can see. In any two, taking any two elements on this lattice, I can find the join point and I can find the meeting point, the least upper bound and the greatest lower bound. So let's say I take, I mean, that's trivial, right? Now you understand. So let's say I take this one and this one. So what, in your opinion, would be the least upper bound for these two guys? So I take 0 and I take that one. So the least upper bound would be, I go up, from here I go up, and we join here, right? And what would be, let's say, the greatest upper bound between these and that? And it's also easy. If I go down and I go down, and we meet here. Right? Okay? People use these lattices with intervals, with subsets, a lot, especially for abstract interpretation. And now finally, abstract interpretation. Abstract interpretation is the mechanism which is supposed to, like I said before, is supposed to help you reason about the program without actually getting down to concrete evaluation of the program. So let's say you have a program which potentially may return number 0. Let's say it's a function. I'll give you a practical example. Let's say we have a function and we take the number from this function, then we pass this number somewhere where number 5 will be divided by this number. So we don't want this number to be 0. So we go to our function, we take something from there, we pass it to somewhere else, and there they use it expecting it not to be a 0. So now our question is, can we decide whether the function in question, which we think about, which we reason about, whether it can return 0 or not? So how do you decide this? I mean, automatically. You can, of course, intuitively look at the function, and with using the piece of paper and the pencil, you can just calculate in your mind, trying to simulate the execution, and then decide, yeah, probably it's not going to happen, or yeah, probably the 0 will go out of there. But we're talking about automatically doing that. So how can you look at the code and, again, without execution, decide whether it's going to happen or not? So they invented, long time ago, they invented abstract interpretation. And they say this is a compromise to be made between the precision of the analysis and its decidability, or tractability, computational cost. So of course you can run this function a million times and passing a million different inputs to your function. And then you will see what is the response, and you will say, you know, on the million inputs, and if for example, you deal with integer numbers, then you can give all the possible integers and then return all the possible answers, and you will say, okay, there is no 0 there, so 0 is never coming out of this function. But it's going to be expensive. It's going to be expensive, and in most cases, it's not going to be possible because it's not going to be possible. It's going to be too many inputs and too long. It will take too long to calculate. So they do so-called approximation, which I will explain you right now. So they say that approximately, we believe that approximately, we predict, we expect, we believe that number 0 will not be going out of this function. But we may be wrong, of course. This, like it says here, there's a compromise between decidability, between the precision. The precision will tell you if the analysis, like we learned before, if the analysis is 100% precise, and it means it's sound, and it will never tell you that, never give you the wrong information. It will never tell you that 0 will be returned, but it will not. So we cannot make, abstract interpretation does not allow us to make sound analysis 100% precise, but we can get close to it. So what is approximation? Approximation. You need to understand what's the difference between over-approximation and under-approximation. I believe you understand what is approximation in general. It's just intuitive term. But let's take a look at over and under. So on the left picture you see, let's say I'm asking you, what is the square of this oval? So what is the square of the orange territory you see on the screen? On the left side you give me the over-approximation. You say the square is approximately this size. So this is the square of this oval. You cannot calculate the exact square, so you give me approximation. But in this case, you over-approximate. You give me too much. In this case, you under-approximate. You give me too little. In both cases, you are wrong. In both answers, you are wrong. But you're wrong in different direction. So and then it depends on the analysis. So it depends on what we're looking for in abstract interpretation. So for example, if I'm asking you, will the function return 0 to me? I may ask for over approximation, or I may ask for under approximation. Let's say I'm going to ask you for, you can tell me that the numbers which are coming from this function will be always will be, let's say, below 100. So you're over approximating. Below 100. 0 is still there. 0 is inside your analysis, inside your over approximation. Is it useful for me? Is it helpful? Depends on the situation. Or you can tell me under approximation. You can say that what the function returns may be, let's say, your answer may sound like, let's say you're telling me that the function returns number 5. While in reality the function will return 0, 7, 3, 5, including 5, and some other numbers. But you're giving me just one number. You're right, the number 5 will be returned sometimes, but you under approximated, because 0 will also be returned, and 7 will also be sometimes returned. But you gave me the right answer, but you under approximated it. So you instead of over approximating and saying yes, 0 and 7 and 5 and many others, so I'm just covering everything, you're just doing under approximation. So usually abstract interpretation is about over approximation, about this. So these are the answers which this abstract interpretation is giving us. They are over approximating. Now, more specific about abstract interpretation. Abstract interpretation expects us to in order to work, in order to deal with abstract interpretation, I'm just moving to it step by step. So I will show you now just two things before we go right into this mechanism of abstract interpretation. The first thing, you need to understand the mapping between concrete domain and abstract domain. So let's say we have the concrete domain. Let's say they are the numbers which are really the program is working with. So let's say these are the numbers which are returned by our function, which we just discussed. So there's the function, and we know that if we run this function, the numbers will be coming out of this function. And we know that they will be, let's say, numbers 12, number 7, number 4, number 0, number -9. So these are the numbers which are which may be returned. So they're concrete numbers. And now we're trying to abstract them. So now we're trying to present them, and usually people do it with the sets, like we just did with this lattice with intervals. And the concrete domain consists of concrete values, and abstract domain consists of sets. So this is the set. This is a set. 3x means 3 multiplied by 1, by 2, by 3. So these are the set which I just wrote it. I just write it this way for compactness, to make it shorter. But in reality, it's 3, 6, 9, 12, and so on. This is the set here. Here it is 6 multiplied by 6. So this is 6, 12, 18, and so forth. This is 2 multiplied by x. 2, 4, 6, 8, and so on. These are 2 in the power, so it's going to be 1, it's going to be, okay, let's say 2, 4, 8, 16, and so on. This is empty set. So in order to deal with my concrete code, it's important, that's part of the abstract interpretation, it's important to define abstract domain. So the concrete domain usually consists of, well, probably infinite number of elements. It's too big, and we don't want to do the analysis dealing with concrete domain of numbers. That's why we're trying to define an abstract domain, which is much smaller. So here in this lattice we have how many? 1, 2, 3, 4, 5, like seven items, 7 elements in our, let's remember this is POSIT. So we have just 7 elements to deal with. So now we will try, if we define this lattice, this abstract domain, we will be able to reason about our program, about its behavior, by looking at only the abstract domain. So we will forget about concrete domain, what were the real numbers, we will just deal with abstract domain and we'll say the program will return 3x, or the program will return this or maybe that, or the program will accept this and then return that. That's how people reason. That's the idea. The whole idea of abstract interpretation is to reduce the size of the domain, reduce the size of those elements which we think about, which we reason about, and then everything becomes simpler. So you don't anymore check the behavior of the function. You just reason. You just expect it to accept one element of your abstract domain and return another element of the abstract domain. And then you tell the user, we expect the result of the function to be, like I said before, below 100. Because below 100 was the category, was the element in your abstract domain. Over approximation, of course. So you over approximate. You don't do exact number. You don't specify. And in order for this to happen in the analysis, they define two functions. They're called the alpha function, which is a mapping from here to here. This is alpha function. And they define gamma function. The gamma function is the reverse mapping. So alpha function says if I give alpha 7, then I map to, let's clean it up a little bit. Let's define alpha function. One simple alpha function. So if I say alpha 7, then 7 goes into probably here. So it means that we don't have, we don't reason this. So it's under approximation in this case. So 7 for us is like an empty set. And if I say alpha 3, then it goes here, the mapping. If I say alpha 8, then it may go here, it may go here, and I decide to go here. The lower, the better. The precision is higher. Because of course all of them may go, and actually I'm wrong, the 7, I didn't do the 7 right. 7 goes in here. So the lower the better. So the lower you put the on this lattice, the more precise will be the analysis. And then you go back. So let's say you take sexx. This is gamma. Gamma from 6x. It goes to 6, 12, 18, and so on. So the mapping from the alpha mapping is mapping from a concrete value to a set, to an element of this lattice. The reverse mapping is also from one element of the lattice to a number of elements on the left domain. So from one to many, from one to one, and from one to many. That's how it works. So this is abstraction function, which goes from the left to right, and concretization function goes back. And they say that there should be the domains, the left and right, the concrete and abstract, they should be related through Galois connection. So this Galois connection means that it's a interesting formula, we can read it, that for any C on the left domain and for any A on the right domain, the mapping, the alpha from C, if the alpha from C goes to some A on the right graph, then it means that we take this A, we map it left, and this, what we get on the left, will be inside the C will be, so we will be able to map back. That's basically how I understand it. But I'm not super expert here. I just understand that there has to be a connection, so if we map from left to right, then it's possible to go from right to left. So they are connected. So we don't just go right and then we never go back. So it's not going to be possible to go back. So by this mapping, we establish this interpretation of this abstract connection. And we are running a little bit of time. So before we go further, there is we need to define abstract semantics. So in order to deal with the program and reason about the program using abstract domain, we need to use so-called transformers, or they call abstract semantics. So we need to define on an abstract domain, we need to the operations on the concrete domain, we need to represent them with similar operations on the abstract domain. So if we say in our program, for example, number plus number, then we understand that when we're going to reason about this program, we're going to replace numbers with elements of the abstract domain. And there will be not any more numbers, but there will be, like in our cases, 2x, 3x, 6x, like sets, like groups of the abstraction. And there will be elements of this lattice. And we need to define on the concrete example. So in the concrete example, there will be, for example, number plus number, and we know the result. It's going to be the number. But if we replace the concrete numbers with abstract things, abstract elements, then n plus n will be probably n, or 2x plus 2x. So if we have two elements of this, then probably the result will be also 2x. If you summarize 2x plus 3x, then probably the result will be n, because there is no guarantee that it's going to be 2x. There's no guarantee it's going to be divided by 3. So probably it's going to be just n. If you multiply 2x but 3x, then you're going to have this block, this element. And if you say this one plus 2x, so nothing and plus 2x, then probably we're going to have again the number. Maybe no. Wait a second. It's going to be also something with no specific information. That's how I understand it. So we need to define, that's the second step. First step, we define abstract domain. Then we define operations on abstract domain. And finally, okay, I'm going to skip that. And finally, we do a few more minutes. Stay with me. So finally, we do the fixed point calculation, so-called. So we take a program. Let's say this is our program on the left. So read it and try to understand what's going to happen. So the question which I'm trying to answer with the analysis of this program is whether the program will do the division by 0. So whether the bug will be there, whether the division by 0 will happen, and on what specific input here. So if I, for example, pass number 2 here, will the division by 0 happen? You can check it yourself, just intuitively. Just go through the code, understand what happens, and you will see that probably it will, or probably it not. So think about it. And what happens if I pass the number 37? Will the division by 0 happen or not? Good question, huh? So in order to answer this question in an abstract way, not just like I'm saying, like I'm asking you to do now, like pass the number and do the calculation in your mind. And then how many more calculations? What if I give you the number of, what if I ask you to answer me this question for the number, I don't know, 1000? And how many more experiments you're going to run in order to give me the final answer? And remember, it has to be a mechanized answer. So it's going to be automated answer. The machine has to give the answer. Not you explaining you intuitively, but you have to create a software. You have to create a decider, a static analyzer, which will give me the answer. So how they do it with abstract interpretation? First, they create a control flow graph. We discussed it before, control flow graph. So the control flow graph, this is an entry point, this is an exit point. So there are statements. Statement 1, statement, or they call basic block. So there are statements. And each statement has something which is coming into and something which is going out of the statement. And then they invent, somehow, they create an abstract domain. So on the right, the lattice. And I define it like this. So all the numbers, all the positive numbers, 0, and then the bottom, and then the error, I put the error here, which is the result of division by 0, and then 1, 2, 3, and 4 or more. So that's a group which is called 4 or more. So then I'm saying, and then what they do is they start going through this control flow graph, bringing from block to block, bringing the elements of the abstract domain. So let's say they start from here and they say, I have this element in my hands. And then they reason what's going to happen after this n on the exit of this block. And they know the semantic of this operation, the abstract semantic, which we just discussed before, from here. So they know how to compare, n, because x is now n. So they know how to compare n more than 0. So the semantic of this operation is known. So we know the abstract domain and we know the semantic of each operation. This operation, we know this operation of these 3 semantics. And now we start dealing with the elements of abstract domain. So we don't deal with numbers, we don't deal with these guys. We do the calculation, we like execute the program. We do like an execution of the program step by step, but having these abstract things, abstract elements in our hands. Not numbers anymore. But n, we just deal with n, 0, 4 plus, this one or that one. And we move block by block, returning back. And every time we return back, every time we return, because we have loops, we have calls, recursion, whatever. So every time we return, we already remember that n was here. So n is written there. And when we return, then we have 2 elements coming together into the block. And because we have a lattice, we now can meet them. We can join them, sorry. So we join them because the n was from there. Then we return using this loop line. We return into the same block with something else, which we already calculated abstract value, which we calculated using abstract semantics. So we return with a new abstract value, and we have another abstract value, which was there before. So we hit them together and we join them. How we join? We discussed how to deal with the lattice. So we join using the lattice operations, operator, using the logic of the lattice. So we join using this least upper bound or, least upper bound. And then we continue calculating. We continue going through the program, moving these abstract values and remembering which of them were at which statement block on the control flow graph. And at some point of time, this calculation, this going through the graph, will stop. Why it will stop? Because no abstract values which we attach to these lines into the blocks will not change anymore. They will be just the same. So no matter how many times more you loop over the control flow graph, all the abstract values will remain the same. And then people say, okay, it's a fixed point. So we can stop. No point of any more going through. And then when you stop, you can say, okay, now we know at each block what is the over approximation of the values which may go into the block and which may go out of the block. And if your abstract domain is precise enough, and if your this abstract semantics is correct, is sound, so-called, so it's also doesn't make mistakes, then you will be able to pretty closely over approximate the behavior of your program. And you will say, you know what, the result of this function will be no more than 100. That's it. That's the idea of abstract interpretation. That's what we do. And people use this approach further and further. We'll use it in data flow analysis, in the symbolic execution, everywhere. That's the idea. So don't deal with concrete numbers, deal with abstract numbers. To deal with abstract numbers, you need to define who they are. So you need to define this lattice. You need to define the operations on the lattice. What is the join, what is the meet, and then define abstract semantics. And then you can go. Then you can do the analysis.